Okay, let's continue our study of group actions. In the last videos, I have defined what it means for a group G to act on a set S. I have told you what orbit of an element is. Orbit of an element is so you take an element of capital S, its orbit is, you apply all elements of the group to that element, fixed element, small s, and you consider the set. Consider the set of where it travels. So orbit of S is collection of GS where G varies over the group G. Small g varies over the group G. And we saw several examples of group actions, and in some of those examples we have seen orbits of specific elements. Okay. So today I am going to start with thinking of orbits as equivalence classes in the following way. Okay. So let us say our setup is the following. So G is a group, S is a set, G acts on S. Right? This is our setup always, a group acting on a set. Define an equivalence relation. First let's say a relation on S as follows. So I'm going to define a relation denoted by this symbol as follows. I'll say that S1 is related to S2. So we say S1 is related to S2. So remember, we read this as S1 is related to S2 if there exists an element in the group G, small g, such that GS1 is S2. Remember, GS1 denotes the action of small g on small s1. So that is how we denote the action. So remember, the action means there is a function from G cross S to S which takes an element G comma S to GS. We just denote it simply by GS. Instead of writing G star S or G dot S, we will, for convenience, denote the action by GS. So now this is the relation I am defining. S1 is related to S2 if there exists a group element such that GS1 is equal to GS2. So now the question is this an equivalence relation? Remember, an equivalence relation is a relation satisfying some conditions, right? What are they? We want every element to be related to itself. You want the relation to be reflexive. So the first condition is S related to S. Yes, because why? Why is S related to S? You can take ES to be S. You have ES is equal to S. This is by the definition of action. So you see that we need this as in order to make this an equivalence relation, we must have this, and this is guaranteed by the definition of group action itself. So identity element sends S to S. So S is related to S. In order for S1 to be related to S2, we want a group element such that GS1 is equal to GS2. We take the identity element of the group which always exists in a group, and ES is equal to S, so S is related to S. Suppose if S1 is related to S2, then is it true that S2 is related to S1? This is the symmetry property, right? If S1 is related to S2, is S2 related to S1? So let's see. If S1 is related to S2, by definition there exists G in G such that, by definition this happens, right? If S1 is related to S2, there exists a group element such that GS1 is equal to GS2. Now let's apply the action properties, and let's in particular apply G inverse to both sides, right? if GS1 is equal to S2, remember these are elements of capital S. These are two elements of capital S that are equal to each other. Let's apply G inverse to both of them. Then by definition of group action, this follows from as before, definition of from group actions. What is the definition? Remember, group actions must satisfy two conditions: ES equal to S and G1 G2 of S is G1 of G2S, right? These are properties of a group action. These are the defining properties of a group action. So G inverse GS1 is same as G inverse GS1, but that is ES1. G inverse G is E, but ES1 again by the definition of action is S1. So S1 is equal to G inverse S2. So that means there is a group element such that that element times S2 is S1. So S2 is related to S1, right? Remember, we say that S1 is related to S2. The first one is related to the second one if a group element takes the first one to the second one. Here S2 is taken by G inverse to S1, so S2 is related to S1. So the question has an affirmative answer. If S1 is related to S2, then S2 is also related to S1. This is the symmetry. Finally, we want to check transitivity of the group action. So suppose S1 is related to S2 and S2 is related to S3. So that means G1 S1 is S2, G2 S2 is S3 for suitable G1 G2 in capital G. Because S1 is related to S2, G1 S1 is S2 for some group element. S2 is related to S3, so G from some group element S2 is taken to S3. Now again we apply G1 G2 to S1. By the definition of a group action, this is G1 of G2 S1. But G2 S1, let's actually apply G2 G1. G1 S1 by hypothesis was S2 and G2 S2 by hypothesis again is S3. So this implies S1 goes to S3 with a group element G2 G1. So S1 is related to S3. So we conclude, we check the three defining properties of an equivalence relation. So this is an equivalence relation, right? So again, let's recall what is the equivalence relation. It says that two elements are equivalent if there is a group element that takes one to the other. So that's an equivalence relation I have checked so far. But now I want to use the definition, the important property of equivalence relation. Recall that an equivalence relation in some sense the most important property for an equivalence relation is that it partitions the set into disjoint equivalence classes, right? We take equivalence classes. When I did equivalence relations and when we talked about cosets in a group, I did this in detail, but so let's not repeat that again. But in equivalence relation, partitions a set into disjoint equivalence classes. You take some element and you look at all elements that are equivalent to it. That's an equivalence class. And the most important property of equivalence classes is that two equivalence classes are either disjoint or they are identical to each other, right? They can't be different and have something in common. So if you take distinct equivalence classes, they are all disjoint, and because every element is in its own equivalence class, equivalence classes certainly cover all of S. Okay, so now In this example of an equivalence relation, now that we have a group action on a set, let us take a small s in capital S. What is the equivalence class? Let's compute the equivalence class of S. Okay, in the earlier situation we have denoted equivalence classes by this symbol. By definition, what is this? These are all T in S such that S is related to T. All elements of the set such that S is related to T. But now I am working with a specific equivalence relation. So these are all T in S such that T is GS for some G in G. Right? Remember, this is the equivalence relation. We say that S1 is related to S2 if there is a G such that GS1 is equal to S2. So if T is supposed to be related to S, then GS must be T for some G. So this is simply can be written as GS for all G in G. Right? I can eliminate the variable T here. As small g varies in capital G, I'll take small gs. But we have another name for that from the last video. But this is simply the orbit of S, right? So this is simply the orbit of S. So the equivalence class of an element is precisely in the notation of the last video is the orbit of S, right? So we have orbit of S, remember, is exactly this set. It is where S travels under the action of G. So equivalence classes for the relation that we have defined today is simply the orbits. So we conclude, hence after all this we conclude that, so the setup is, if G is a group acting on a set S, then the set S is partitioned you take the distinct orbits under the G action on S. Okay, so this is a elaborate sentence, but it is the conclusion of what we have done so far. If G is a group acting on a set S, then S is partitioned into distinct orbits by the action G action of S. So in other words, S is a union of orbits. So that we know because every element is in its own orbit and two distinct orbits are disjoint. This is because being related under G action is an equivalence relation, so distinct orbits are disjoint. So we have the picture as I have drawn earlier. So you have a set S, so you have OS1, that's one orbit, OS2. In general, an equivalence relation partitions a set. In our situation, equivalence classes are orbits, okay, and so on. So this could be infinite, of course. I am trying to just illustrate this. Orbits, number of orbits may be infinite, but each individual piece in this partition is a single orbit and they have nothing in common. Two distinct orbits have nothing in common. This is the first important observation about group actions that we will exploit a lot. Okay, so this is an important fact. So this is important observation. As we will see later, we will make use of this observation in the future videos. Okay, so now let me introduce another important notion, object attached to a group action. So let now consider a group. I'll come back to this partition of a set into its orbits later, but now for the moment consider a group G acting on a set S. Again, let me repeat for you. G is a group acting on a set S. So G is an abstract group, it can be any group, and S is just a set. Even when S is equal to the group itself, it is really just a set. Okay, so for let us fix a small s in capital S. I have defined for you the orbit of S, right? OS. Now I will define something else now. The stabilizer of S is the set of elements is the subset of G defined as, okay, so stabilizer is denoted by G sub S. Remember, we have orbit of S was denoted by OS. Now I am defining stabilizer as G sub S, or sometimes I will use steb of S just for clarity. This is a subset of G. Unlike the orbit, orbit is a subset of capital S. Stabilizer as a in the definition, it's a subset of, it is more than a subset actually, but as a we first define it as a subset. It is all group elements that stabilize. Okay, think of this as stabilizing S. So G does nothing to S, G fixes S. So this is the set of group elements that fix S. Okay, so this is the group elements that fix S. So the immediate lemma that I will prove immediately is GS is not merely a subset of the group, it is a subgroup of G. It is a subgroup of G. What is the proof? We have now done so many examples and results to check a group subset is subgroup. So let us quickly do this. This is very easy. We have to check that the identity is there. It is closed under a multiplication and it is closed under taking inverses. First property, E times S is S by the definition of group action. So E fixes S, right? So E is in the stabilizer. Stabilizer is all G such that GS is equal to S. So stabilizer contains identity element. Let's say G1 and G2 are in the stabilizer of S. That means G1S is S and G2S is S, right? This is the definition of being in the stabilizer. Now what is G1, G2 of S? This is by the definition of group action is equal to G1, G2 of S, which is equal to G1 of S, because G2 of S is S. G1 of S is also S. So this implies that G1, G2 is in GS. Right? So if two elements are in the stabilizer, their product is in the stabilizer. That's good. So stabilizer is closed under multiplication. Let's say you take an element G in the stabilizer, then what is GS? That's S by definition of being in the stabilizer. Now if you multiply both sides by G inverse, I get this, but this is same as G inverse G of S is G inverse S, but that is ES is equal to G inverse S. This means S is equal to G inverse S, right? But this means that G inverse is in the stabilizer of S, because G inverse also fixes S. G inverse S is S, so G inverse is in the stabilizer. So this is the proof that stabilizer is a subgroup of G. So I want to make this important note here. So given an action of G on S and an element small s in capital S, we have two things. We have orbit of S, which we denote by OS, which is all GS as G varies over G. This is inside S obviously, and we have stabilizer of S that I sometimes denote by G sub S, sometimes by stab S. This is all G in G such that GS is equal to S. This is a subgroup of G. Right? This is the situation now. So we have attached to a single element of capital S something called orbit, which is a subset of capital S. Remember, capital S is just a set, so we can't talk about a subgroup or anything like that. It is just a subset. Stabilizer is a subgroup of capital G. So there are two things. So stabilizer, and I will do in a later video examples of stabilizers in more detail.